All right, this is 11.3 and we're going to be working just with area today, and we're going to be doing area of polygons. So two specific polygons that have formulas for area are rhombuses and kites. That is something that we did in a previous chapter. So a rhombus, as a reminder, is a quadrilateral, which is a polygon with 4 sides. So it's a quadrilateral with 4 equal sides. And specifically bisected diagonals. So the sides are all equal. So here the sides are all equal and the diagonals are bisected. So here's one diagonal. So these two things are equal. And here is the other diagonal. And that is split into 2 equal pieces as well. So these show the diagonals. So D1, that's kind of the length of that first diagonal. D2, that's the length of that vertical diagonal. So a kite is a quadrilateral, but specifically with 2 pairs of congruent adjacent sides. So they have to be next to each other. And 1 bisected diagonal. So that's just kind of a reminder of what the kite and the rhombuses are. So these are the 2 adjacent sides, these are the 2 adjacent sides, and this diagonal right here is being bisected. So that's representing D2, that's D1. So the formula for the area of a rhombus or a kite is actually the same for both. The area of a rhombus and the kite is 1/2 the product of the diagonals. So 1/2 D1 times D2. All right, now we're gonna be moving on to regular polygons being inscribed in circles. So a regular polygon is a convex polygon. Remember, convex, it's not caved in anywhere. So a convex polygon with equal sides and angles. So all of the sides and all of the angles are equal all the way around. So these can always be inscribed in a circle. So if you have a regular polygon that's the same all the way around, you can always put a circle in it. So here's a regular hexagon, and all of those vertices fit perfectly on the circle. So there's a couple pieces. There's the radius, which would be from the center to the vertex. So the radius is the distance from the center to a vertex. And then there's the apothem. The apothem is something new. So the apothem is from that center to the edge. the edge, not of the circle, but the edge of one of the sides. It makes that right angle. So the apothem is the distance from the center to the midpoint of a side. And it bisects that side at a right angle. So any regular polygon that you do this to, you're going to get the apothem. It's going to be a perpendicular bisector. And then there's one last piece, and that is the central angle of a regular polygon. And that is this right here. That is a central angle. So the central angle is created by two adjacent radii. So in this case, you would have a central angle MPN. So that's a central angle right there. And the measure is 360 divided by n. So n is the number of sides. So here, this central angle, this is a hexagon, so it has 6 sides. That measure would be 360 divided by 6, which is 60. So let's kind of use that. So in the diagram, WXYZ is a square inscribed in circle P. So we want to name the following. So what's a radius, what's an apothem, and what is a central angle? So the radius, there's actually two of them that's drawn. There's PX and PY. There's an apothem that's drawn, so it's from the center to the midpoint of a side. So in this case, PQ is an example of that. And the central angle, so two adjacent radii, XPY. All right, so now we're actually going to use that to find some of the angles. So in the diagram, ABCDE is a regular pentagon inscribed in the circle, so find everything that's, find all these angle measures. So it's a regular pentagon, so it has 5 sides. They're all equal. So what would be the measure of AFB? So AFB is this whole angle right here. So that's the central angle. Which we get by doing 360 divided by n. 360 divided by how many sides? A pentagon has 5 sides, so 360 divided by 5 is 72. So that's 72, as well as all of these are going to be 72. Then we have AFG. So that's just half of it. It's actually bisecting it, so it's going to be half the central angle. So 72 divided by 2, which is 36. And then lastly, we have GAF, which is right here. And that we can kind of look at this right triangle we've created. We have a right angle. This is 36. So A would be whatever is left over. So 180 minus 90 minus 36, and that's going to give us 54. So these can be really useful. Essentially, you're splitting a regular polygon into different pieces, into different, just smaller triangles. Okay, and now please go and watch part 2.